In this video, we are going to see about modeling of practical transformer. So first, we will see how to represent the non-ideal parameters, then the step-by-step procedure to model the practical transformer. And we will also see the equivalent circuit of the practical transformer on no load and loaded condition. In the previous video, we have assumed that for an ideal transformer, the core has infinite permeability or a high constant permeability. There is no winding resistance, no leakage flux, and no core loss. But ideal transformer doesn't exist in the world. So in the practical transformer, we have to consider all these factors. So what we are going to do is, in a practical transformer, the core will have finite permeability and there will be winding resistance in both the primary as well as secondary, and there will be leakage flux and core loss will be there. So considering all these factors, we have to design or model a practical transformer. So the first thing we are going to consider is the core has a finite permeability. So what does it mean? If you take the BH curve of the magnetic material used for the core, if it is along this line, it has lower permeability. What we want is along this y-axis. It means that it is an ideal case because the slope of this curve will give you the permeability. So mu r is equal to del B divided by del H. So if it is to be high, our slope should be here along the y-axis. So how it is going to affect you? We know H is equal to Ni by L. So if N is constant, so I will be somewhere here. If I choose this line, I will be minimum. Okay, if my graph is here, I need more current to magnetize the core. So the magnetizing current is going to be affected by this core permeability. So we have to add this magnetizing current component to the ideal transformer. So we know ideal transformer on no load, the magnetizing current requirement is less, very small current or a negligible current is taken. And we have already seen about this phasor diagram. So this is the supply voltage V1 where the flux will be lagging or the magnetizing current will be lagging the supply voltage by 90 degree. And E1 and E2 are the voltages which will be in antiphase with V1. Depending upon the turns ratio, E1 magnitude and E2 magnitude will change. So if you load the transformer now, so if load the transformer here, it is going to draw some current I2. So I have taken a lagging load, so current is here. If I take a leading load, current should be leading the voltage. So here it is lagging. Now this current, when it flows to the secondary windings, it will produce an MMF N2 into I2. So when an MMF is developed, a flux will be created and this flux, secondary flux, will be opposing the main flux, mutual flux. So the primary has to draw more current to compensate the demagnetizing effect of the secondary flux. So what happens? This N2 I2, due to this I2, N2 I2 will be there. This should be compensated by a primary current. So initially we saw that when there is no load, only a small magnetizing current flows. So now the primary will take some additional current I2 dash to compensate the secondary MMF. So N1 into I2 dash. N1 is the number of turns in the primary winding into this current will develop an MMF which will cancel the secondary MMF N2 into I2. So this I2 dash will be in antiphase with I2 and Im plus I2 dash. If you find the addition, you will get I1. So I1 lags V1 by some angle phi. So now we can see that Im is at 90 degree here and it lags the voltage, supply voltage by 90 degree. Okay. So the magnetizing current is lagging the voltage by 90 degree. So how to include this in the equivalent circuit? You have to add a magnetizing reactance here. You see the current, there are two parts in a current. So we know under no load condition Im was there, but when it is loaded, it needs some more current which has to flow through this N1 winding. So I2 dash flows through this path, Im flows in this path. So this is called the magnetizing reactance. So we are including this magnetizing reactance to show that the core has a finite permeability. So we can write Im is equal to Vn divided by Jxm, or instead of J I can write angle 90 degree. So where Xm is called the magnetizing reactance and it should be a very high value because Im is a very small value. Next we will add the winding resistance R1 and R2. So we know both primary and secondary winding will have some resistance. So let us take it as R1 and in the secondary side it is R2. What happens when current flows through this winding? I into R, voltage drop will be there both in primary and secondary. So I have to add resistance in both primary and secondary. So this is shown here R1 and R2. Since current flows through this path, it should be included here, not in a parallel line. Okay. So the total current flows through this resistance. I1 into R1, here I2 into R2 will be the voltage drop. So here, once you include this resistance, though it is a very small value, V1 is not always equal to E1. So V1 will be equal to this drop plus E1. Okay. And similarly, E2 is equal to I2 R2 plus V2. Next, we have to add leakage component. So we know total flux is equal to mutual flux plus leakage flux. Mutual flux or a main flux is the total flux which remains constant in a transformer or which flows in the core. Okay. Now, apart from mutual flux, there will be leakage flux. Like this is a flux which which will not link with the secondary. So it is produced by the primary MMF and it doesn't link with the secondary. So which directly passes through the air. So it is called a leakage flux. This mutual flux leads to energy transfer while leakage flux will not contribute to any energy transfer, like water in a bucket. So the water inside the bucket only will help us to do some work, whereas whichever flux which has leaked out is not going to help us. Same thing. Okay, not only primary flux, the flux in secondary side also, this secondary MMF will produce some flux which will be linking with the secondary alone, not with the primary. So there will be secondary leakage flux also. So there will be some secondary leakage flux. So let us see how to add this leakage component into the equivalent circuit. So the voltage induced in any coil, we know E is equal to N into d phi by dt. Okay, this is a general formula, Faraday's law. So this flux, now we am telling I have mutual flux plus leakage flux. Okay, so here N1 into d phi by dt is equal to I have mutual flux plus leakage flux. This is for primary winding alone. So let us split this one. So it becomes N1 into d phi by dt plus N1 into d phi by dt. This is leakage flux. This is due to leakage flux. So this flux contribute to energy transfer, while this will not contribute to any energy transfer. So it is mere a voltage drop. So the leakage flux leads to a voltage drop which can be represented by a inductance. So here reactance XL1 and here in secondary side it is XL2. So when current flows through this reactance is going to create a drop in it. So V1 is equal to E1 plus I1 R1 plus J into XL1. So similarly, secondary side also we can write the equation. Next, we have to include the core loss component. So the core plays a major role in a transformer, and all the flux will be flowing through the core. So here the flux through the core is alternating. Because of that, we have two type of losses in a core. One is the hysteresis loss, the other one is the eddy current loss. So hysteresis loss is due to the magnetic property of the core. That is, the loop should be very small or it should be a single linear line. The loss will be less. And this is the other thing is eddy current loss. So we will talk about the losses in separately. Okay. So we have two type of losses. This core loss is actually dependent upon the supply voltage and the frequency. As our supply voltage and frequency is almost constant, the core loss is assumed to be constant for different load conditions. Okay. Let us include the core loss component. Because we know core loss, when current flows to the core, it gets heated. So there is a heating effect is there. So the core loss component is represented by a resistance RC. So it is shown here. So even under no load condition, the transformer has to supply the core loss. So because at that time also flux will be there in the core and current will be flowing in the primary. So we need to supply the core loss during no load condition also. So no load current is given by, you can see here, since there is no secondary current, I2 is 0. So if there is no I2, no I2 dash will be here. Only IM will be there. So here I1 is equal to I0, where I0 is equal to no load current I0 equal to IW plus IM. IM we know it is the magnetizing current which we have seen earlier, and IW is the core loss component of no load current. And this if you see the phasor diagram, IW will be in phase with V1, IM will be in quadrature with V1. So the summation of these two will give you I0. So let us recall what we have seen so far. For modeling of a practical transformer, first you have to consider the core permeability, which is represented by a magnetizing reactance X. Then to include the winding resistance, we included two resistors R1 and R2. And then to include the leakage flux, we have two reactances X1 and X2. Then to include the core loss, we have the resistor RC. So in the next video, we can see about how to draw the phasor diagram for a practical transformer. If you like the video, do subscribe to Read Electric Vehicle channel.